We're looking at the oxygen cascade, basically how oxygen partial pressure changes throughout the vasculature. And we're looking at pressure here in millimeters of mercury. And then at the bottom here, we're looking at the location. So what area of the vasculature we're speaking about. So we can go from the atmosphere on the left to the mitochondria, which is the final destination of oxygen. Okay. Okay, and we know that we start out at 160 in terms of our highest recorded partial pressure. So we start off at 160, and this we can label as the atmosphere at 160. And then there's a significant drop off between the atmosphere and the alveoli. And this drop off has to do with several factors. So for one, we've got the conducting zone, which we described as being that dead space region. So we have some air that's present in the dead space that has already participated in gas exchange. So mixing of the air is one of the factors that's responsible for this drop off. The second factor is what else that happens along the conducting zone? What's something else we said the conducting zone helps with? Humidifying, yeah, so humidification of the air as it's moving through that part of the bronchial tree. So that addition of water, that addition of moisture to air is another reason we see this, is another reason we see this large drop off in the partial pressure, okay? All right, so from the alveoli, again, we drop off partial pressure, eventually down to the level of the capillaries. And by this time, we're at about 40 millimeters of mercury. And then eventually we go down into the cells and down into the mitochondria. Okay? And so what we can see here is that the direction of flow is in this way, right? So the diffusion gradient takes place from the atmosphere down into the mitochondria, okay? And we can make a note here that the partial pressure of oxygen gradient favors the movement of oxygen from the atmosphere to the mitochondria. Okay? All right, and I will expect you to know these, right? That the atmospheric pressure is 160, in the alveoli it's 100, and at the level of the capillaries it's 40. Ready? Okay. Any questions on this? Yep. Here? 160? Here? Here? Oh, sorry. Partial pressure, millimeters of mercury. So PO2 and millimeters of mercury. Sorry about that. Okay. We can also look at the same type of graph for CO2. All right, everyone done with this? Yeah, okay. So we can also look at the similar graph for CO2. And now we know CO2 is moving in the opposite direction, right? It's going from the tissues out to the atmosphere. And so our gradient is going to be starting high at the level of the tissues and going very low at the level of the atmosphere. I'm sorry, CO2 cascade. All right, so this is the partial pressure of CO2, and that's again in millimeters of mercury. Okay, so we start off here at about 0.3 millimeters of mercury, and this is in the atmosphere. And then by the time we get to the alveoli, we have an increase again. So the alveoli has a partial pressure of 40 millimeters of mercury. This was 0.3. Okay, and then we eventually increase as we go through the systemic veins and pulmonary arteries, and then again up to the capillaries and up to the cells. At this point, it's about 46 millimeters of mercury in the pulmonary arteries and systemic veins. And then eventually we get to the capillaries and then the cells. Okay. And again, these values are what you should be able to connect, right? Atmosphere is 0.3, alveoli is 40, and then in the systemic veins and arteries, we got 46. And the increase here is much smaller. It's going to be a little bit more minimal between the cells and the capillaries. Okay, and so what we see here is a gradient in this direction, right? From 46 down to 0.3. And so this is the diffusion gradient of CO2. So we can also make a note here that the partial pressure of CO2 gradient favors the movement of carbon dioxide from cells to the atmosphere. Okay, so we've got a gradient for the partial pressure of CO2 occurring in the opposite direction.